Here an NCEA question from 2017 that is a fun question. It looks a bit complicated, but it's actually quite straightforward when you look at it. Sam's got a flying fox, a zip line that he wants to use in the dark. Here's his tree house and he wants to get down to this tree. So in order to use it in the dark, he connects a battery with a spotlight on it. He said he used a 12-volt battery, 12 volt, connected to a spotlight using two 1.6 meter long wires. So here's Sam, here's his zip wire, and here is his electrical circuit. He's got his battery going up 1.6 meters to the spotlight and then back down to the battery. Here's the circuit diagram of it. From the positive terminal, the current's going up there through the bulb and back down to the negative terminal of the battery. We're asked to calculate the force, including the direction due to the Earth's magnetic field on the 1.6 meter long wire connected to the positive terminal of the battery. And it's this lower left end here. So let's have a look at the overall picture. We've got Sam doing his death-defying thing with his battery and spotlight, and at this point the magnetic field is going into the page, which would be parallel to the Earth at this time, and here's the Earth's magnetic field, 30 microtesla, and we remember micros 10 to the negative 6 Tesla. So Sam connects a 12 volt battery spotlight using 1.6 meter long wires, 1.6 meter long wires. The light and wires have a combined resistance of 2.4 ohm. In our circuit, the bulb has 2.4, bulb and wires 2.4 ohm resistance. Sam sits on top of the flying fox inside the Earth's magnetic field, which is horizontal and has a magnetic field strength of 30 times 10 to the negative 12. Our question is, calculate the force, including the direction due to the Earth's magnetic field on the 1.6 meter long wire connected to the positive terminal. So it's this wire here. What's the force on that? Now we've got a force, we've got a length, we've got a magnetic field strength. So at some point we're going to use F equals BIL. We want to find the force. We're given the Earth's magnetic field strength. We don't know the current, but we're given a length. So our first task is to find the current. We've got our circuit here. We're given a circuit and we've got a voltage, we've got a resistance, and we need to find the current. So what will we use when we've got those three things? Ohm's law. So with our simple circuit here, wanting to find the current using Ohm's law, I is equal to V over R. So the current is equal to 12 volt divided by resistance 2.4 ohm. So the current is equal to 5 amp. So come back to the situation of Sam coming down the zip wire. He's got his wire cutting through the magnetic field, crossing the magnetic field lines. So we can use the force on a current carrying conductor through a magnetic field B, current I and length L will give us that force. So we've got force is equal to the magnetic field strength, which is 10 to the negative 6 Tesla, times the current, 5 amp, times the length, 1.6 meter, equals the field strength is 30 times 10 to the negative 6 Tesla times 5. The answer is 2.4 times 10 to the negative 4 Newton. That's the force on the current carrying conductor from the positive terminal of the battery up to the bulb. And what then is the direction? Let's look at this diagram here. The current flows from the positive terminal through to the negative terminal. So when we look at here, the current is up. Let's try a right-hand slat rule. Right-hand slat rule. The current is up. The magnetic field, without lots of fingers, is into the board, into the page. So the force on that is to the left. Force to the left. So this is an example of a multi-part question where we need to solve for the current first using Ohm's law, then we can apply it in this equation here. Simple enough?